Okay, so that's just no good. Neo-Hookean, no good. At least for rubber. Yeah, that's science. You have a model, you have experiments, you try to reconcile them. If you can, good. If you can't, you have to drop the model. It hasn't stopped the neo-Hookean model to be super popular. That's because it's so simple in its form that you can do a lot of mathematical progress. And people like to solve equations, right? You solve equations, you have nice solutions, and they're all analytic. So you can just write a nice paper and maybe try to explain a phenomenon. But at its heart, it's very far from reality. It should be abandoned. Okay, so what to do? Try another. Try Mooney-Rivlin. That's the other example I gave you. Would that work for this data? Mooney-Rivlin, which reads like this. Isn't it amazing that we did all this very complicated theory to, in the end, just arrive at having to differentiate W with respect to R1, W with respect to it. The final mathematics are very simple, at least for the tensile test. That will predict that the stress strain predicts that the stress strain relationship should be like this, or the stress stretch. So there's the 2, and that's going to cancel out with those halves, and there's going to be lambda 2 squared minus lambda 1 squared, and then the derivative of W with respect to I1 is just going to be C1 minus 1 C2. And what happens then? Can I get a better fit now? And I'll show you what happens then. Let's look for it. Here it is. So again, if I do, what's the difference here? Yes. So here I was the neo-Hookean. I could only do a fit on the first 5 points, and even then I wasn't great. Now with the Mooney-Rivlin, it's again a curve that grows slowly, not enough to capture the stiffening at the end. And so the global fitting is going to be terrible. In fact, it'll be even worse than the neo-Hookean. But for the early part, for the first 8 points, you get a pretty good fitting. And 8 points, that's far, right? That's all the way to 5. Means the rubber has been stretched 5 times its original length. If I look at the errors, they are much better. Well, 5 is bad actually. 5 is at 20%. But if I look at from 1 to 2.2, 2.1 here, the error is very low, right? It's less than 3%. Of course, if you do atomic physics or quantum mechanics, you're going to say 3% is terrible. For us, 3% is very good, very good. So, and then it just goes explodes. So Mooney-Rivlin is not so bad if you were to be interested only in the early part of the formation. If you're not interested in the wider regime where the material stiffens, but you're interested in, you know, deformation that can go up to 100%, double the length, well, Mooney-Rivlin is very good. And so we should keep it in mind. Very good. Oh, I should switch to my notes. For small to moderate regime up to lambda is to 100% extension. And the reason why that is in fact quite you could show that quite visually. Now, if I look at this here, the data is what it is, and then I must do you know, correlation exercise, a minimization exercise, a fitting exercise. I must play on those constants here, C1 and C2, and find the best set of C1 and C2 that will bring the theory and the data together, or as close as possible, and measure the difference between the two. That would be the error. So if I look at this, that's pretty hard, right? The relationship between sigma and lambda is highly nonlinear. There's lambda squared, there's lambda minus 1, lambda minus 2. And it's easy now to implement that into a calculator or into a computer. But at the time, in the 40s, 50s, when Rivlin was looking at all this, it was much harder, right? There was no calculator available. You had to do this fitting by hand. And at the time, then you had to do linear fitting, right? If you have data and you want to fit a straight line through it, that's easy. You can do it analytically. You can find the best C1 and C2 to do that. So he looked at this formula and tried to turn it into a linear formula. And so what he did, he introduced define y sigma 1, 1. So that's a quantity that you can compute from the data, right? Because the data is sigma in terms of lambda. And x is 1 over lambda. That's also another quantity you can compute from the data. And plot y against x for the data. If rubber can be modeled by Mooney-Rivlin, then I will expect, if I look at this formula here, what I'm framing now, that y is related to x as follows. Plus C2x. Yeah, this is what I will expect. Because if I divide the left-hand side sigma 1, 1 by lambda squared over lambda minus lambda minus 1, I get y on the left, and on the right, I have C1 plus x times C2. And so I will expect that this data gives me a straight line. And that's what you do. You plot x against y with the data. So it's just manipulating the points, and you will get a curve that goes like this. So it will start at 1, when lambda is 1, and then when lambda increases, when lambda is 2, is x going to be 0.5. When lambda is 5, x going to be 0.2, and so on and so forth, right? So when you do that plot with the data, you do get, indeed, a straight line. And then what happens, I'll show it to you now. So I have it here. So I've done that for you, but you can do it very easily. Oh no, wait, I can't seem to find it. Sorry about that. So you get the straight line, and then as the material stiffens, you will get a stiffening of this data. And so here, in the beginning at least, you have a straight line fitting. And that's why it's pretty good. Oh, sorry, I should go back. Right. That's why Mooney-Rivlin is so good between lambda is 1 and lambda is 2, or between x is 1 and x is 0.5. You really see a straight line from the data. Okay, and I'm nearly there now. I want to show you what happens what you do if you wanted to capture that stiffening, the one at the end there, where it becomes really hard to pull. Well, if that's what you're interested in, then you should try the Gent model. If you remember, we had this intuition already that the Gent model is going to lead to a barrier, to an asymptote into the amount of stretch that the material can take. The Gent model here is like this: W minus mu 0 Jm over 2 . If I put this now into my formula for the stress, the one I have here on top, W2 is going to be 0, W1 is going to be the derivative of the log with respect to I1, predicts that sigma 1 should be, I have it here, that 1 over 1 minus minus 3. Oh yeah, that's I1. Yeah, I should have written it here. Here I have B, so I1 is the trace of B. It's going to be lambda 2 squared plus 2 lambda minus 1. So this is why it's appearing here. Lambda 2 squared plus 2 lambda minus 1 divided by Jm. If you do that, you'll be able to capture the stiffening pretty well. On the other hand, at the beginning, it won't be so good, the fit. And so good for large stretch stiffening. Not so good for early part. And then when you see that, you tell yourself, well, the Mooney-Rivlin is good for the early part, the Gent is good for the later part. Why don't I combine the two? So, and that's what modeling is about, right? It's just an art. You just come up with ideas like this and you give them a try, and if they work, you keep them. So why don't we try this? Something that combines both models. This part here to capture the strain stiffening, and then this part here to give me that descending slope at the beginning. Combine Mooney-Rivlin and Gent. And when you do that, it's just amazing. It just works perfect. You have now 3 parameters, so you have to first you have to compute sigma 11. So sigma 11, that's going to be easy. It's going to be what I have above there, where I can factorize to minus lambda 1. Minus 3 over Jm plus plus C2 lambda minus 1. So now I have 3 parameters, C2, mu0, and Jm to play with. The curve fitting exercise now is not going to be easy. It's going to be a nonlinear curve fitting exercise. But software will do that for you. If you use R, for instance, it will give you tons of options to do this type of curve fitting. Or even Maple, Mathematica, MATLAB, they will have options to do that. And then just to show you what it looks like, in the end, you'll end up with this amazing fit everywhere. So stress by for the Cauchy stress. You can see that it captures the early part and then the stiffening part. And if you look at the error, it's also pretty good. It's below 6% for the whole range, right? In the later part, it's below 3%. In the early part, it's about 4 to 5%. But it works. Nice. I know it's very elementary, but you'll be surprised how excited people get about this type of modeling and results. There's probably for 80 years now, there's been the search for a good strain energy function that will model that will capture the behavior of soft tissues, soft materials. Okay, I see I'm running over time now, so it's probably best I stop. Do you have any questions? Oh, here's a question. Sorry, I missed that. When choosing P, we wanted stress sigma 2 to be 0, so stress on those faces is 0, but the areas still change. Yes. So you're where is my you are applying a force on the top and the bottom here, but there's no force on this and that direction. So those faces, the one that's facing you is free of any force, and yet it's deforming. Yeah, it's free of force, but you can see that the width is decreasing as I increase the force. Wide, thinner. So the areas change. You can apply one force, you can apply a force everywhere. You can apply one force and leave the other faces free of traction, see what happens. Okay, any other question?